Well, hi, good morning. We're going to continue with the last lecture. I'm not sure why the video doesn't show up on the web page, right? It's actually there, but so before we proceed, I want to give a little bit stuff about the homework project, right? I'm not sure if how many of you have finished and stuff, and I want to give a sense of what is required, what are the different components, right? So you have a notion of a hard disk that we've been looking at. It has sectors and tracks and stuff, head location and stuff like that. So there are a lot of things I want you to simplify because you don't have that much time. This is a two week kind of project. So I'm not expecting you to go too much into any one component. I want you to get the big picture of what are the important aspects, right? So in the class we talked about, when you do the seek and everything, you can compute precisely. So for example, if you want to go from say here to here, and the disk is sort of rotating here, right? You only need to go from here to this little stuff. So as opposed to something going here, right? From this location to this location, it's closer than from this location to this location because you don't have to do as many seeks, as many going through the different tracks, right? We're not doing that for this assignment, right? But be aware that you would typically, you would actually do that. You try to make sure that this is actually only going through one track, and this is going through potentially many tracks to get here, right? But the first component basically tells you what's the cost of going from here to here, and you can leave it simple for now and make it complicated later. But it figures out from the head location to here how much should it cost, right? So that's the first component. What you really want to do is figure out some way of storing files and directories, and I didn't specify how you should do that. So whichever one works for you is good. So one I'm giving example here is where you have set of data blocks, right, which have pointers to all the where the actual data is, and the last pointer points to the next directory entry and so on, right? So this way you can grow the file as big as possible, and if you want to do seek, you have to follow these pointers, so you may have slow access, right? So I'm not making any claims that it's fast or anything, but it's simple to explain. So you have to have a notion of a directory, right, pointing to this file structure, which has a bunch of pointers, which actually has notion of data, right? So if you see a trace like this for the first time, right, and you have a clean disk, meaning your free list is completely empty, what you would end up doing is you have to first create the directory, right, because the directory is completely empty. So you would create the directory, meaning you would have to allocate it, meaning you would have to mark somewhere here where this block should come from, right? And you may choose to do it sequential allocation or however you do allocation here. Let's look at sequential for now. So you allocate this for the directory, right? And then you need for the files data structure. So you need a bunch of pointers, right? 1024 means you need 1024 blocks. If you assume each block is 1K, right? So you would have to figure out how many pointers can fit into one block. So if you assume one block is 1 kilobyte, and if you assume one pointer equals 4 bytes or 32 bits, right? Do the math and figure out how many pointers would go here. I think you can get 255 pointers, right? So for the first 255, you need to allocate one of this, let's say 2, right? And then for the first 255K, you have to allocate one of this. So you keep allocating stuff here, right? And then when it grows, you need to allocate a new one of these structures and some of this stuff, right? So these are the stuff that needs, operations that need to be done, right? Need to be done to implement a system. So when you do a write, you need to allocate all this stuff, and you need to do all this writes, right? And once you generate all the writes that you want to do, basically all the stuff that you have allocated here for this particular operation, you will send it off to the disk. And your disk scheduling algorithm is basically trying to play games with it. So the simplest scheduling algorithm is it just looks at the last one request. and it can decide what to do with that, and it's very trivial, right? If you have only one thing to choose, choosing that one thing is not hard. So if you look at the last 10 items, you can implement any number of policies. You can do, scan, cscan, look, clook, SSTF, whichever one you want to do, right? And that will reorganize. If you made a request of 1, 2, 3, 4, 5, because that's how you allocated, that's what your this part of the program is creating. This you will reorganize it for whatever reason to 5, 4, 3, 2, 1 or something, right? And then you'll figure out using the scheme, the first function, how much time would take for this particular stream, right? Depending on where your head is, how much time you would take the stream, right? And all we care about in the exam, in the simulator, is this component, right? All this other stuff is how it happens conceptually, not necessarily actually, right? You don't have a disk, you're not writing anything into a disk, none of this stuff exists, right? So you need to figure out a way to calculate all the accesses that would happen here without actually writing anything to a disk. There's no disk, you don't have to write anything, you don't have to read anything from a disk. You could store this in memory somewhere using pointers or whatever data structures you choose. But nothing ever gets written to a disk, so don't have to figure out how this picture and all is there to explain how things work, right? The notion of pointers and all those things are there to explain what you have to do. But all we care about is how many operations have to happen, right? So let's take a simple case of 1W, right? 1W would mean that, if this is the only thing which happens, first you have to create this, right, the directory entry. Then you have to create the entry for the file, inode or whatever data structure you use. And then it's only 1K, right? So it will fit into one of those. So essentially your figure will look like this, right? So you allocated this somewhere, and suppose you allocated them as 1, 2, 3, right? So essentially this operation would require 3 writes, right? The first write is for the directory entry, second write is for the file entry, and third write is for the actual data block. And so you may create the entries, assume 1, 2, 3. If you assumed it, if I get it sequentially, you may generate a write request of 1, 2, and 3. Your disk scheduling algorithm can do whatever with it. You can leave it as 1, 2, 3, and that's the, I think, first come, first serve, right? You can implement any different way of doing that, right? And then you figure out, based on where my head is, what would the amount of seeks be for this operation, right? So if the next operation was 2, 1, W, what would happen? Right? So the first one was 1, 1, W, meaning file 1 was created, right? A new file was written. If you want to write the next file 2, what are the set of operations that you would need? This component is actually what happens on the real disk. We're just trying to abstract away all the other stuff, but conceptually this is what would happen in a real disk. If you want to create a new file, what would happen? Yeah.
If it's in the same directory, you just need a file entry and a data block. You don't need another directory entry, the same directory.
You don't need a directory entry, right? But do you have the directory entry? Like, can you modify it, right? If you assume caching and stuff, you can assume that the directory entry was already read, right? For simplicity, assume there's no cache, because then that's another thing you need to add. If you have no cache, essentially you have to first read this entry, right? You're not actually reading anything, but you would have to read this entry to get this structure, and then add the 2, right? And then create this one, and then create this one, right? And then write the directory entry back. So this will create 1 read and 3 writes. Does that make sense? The first one block write took 3 writes. The second one block write would take 1 read and 3 writes, right? Because the directory is actually on the disk, right? So you would have to read the directory entry off the disk, add a new file, and then write it back, right? So it may happen that all these blocks are full, so you may have to allocate a new directory entry or whatever, right? So if you also had this as pointers, and you have to chase this stuff to see how many reads you would do, right? You would read this, conceptually you would read this, see if the file you're looking for is in that one, go to the next one, and so on, right? Is that clear? And that's the important part of how the disks work. I mean, disks, when you have to write an entry, it has to first read the contents to modify the contents and write it back. Yes?
Are we assuming just one directory in this case, or just one root directory? Or?
I'm leaving it entirely up to you to figure out how to make this stuff simpler. So I want you to capture this notion, right? I'm leaving it up to you to figure out whether you want this file structure to be a simple pointer thing like this, or whether you want it to be a inode kind of, server indirect pointers, 1-level pointers, 2-level pointers, 3-level pointers, right? And same for directories. I'm leaving it up to you to figure out if you want multi-level directories, how you want to implement that, or what have you, right? In general, I would suggest that you should make it as simple as possible, right? But the important thing is to try to figure out what set of operations would happen for actual file, why you would optimize for these things and all. Yeah.
For the allocation for directories and subdirectories and stuff, do we have like a standard size that we're supposed to allocate? Is it just like one sector or something like that, or is it?
It's multiples of sectors, and from an OS perspective, we call that blocks, right? And you have to assume something, right? I don't think I specified that in the thing, right? Typical sectors are 512. Typical blocks are whatever when you create a partition, you create it as, right? It can be 1 or 8K, right? 1K, 8K, it can be whatever you want, right? And you have to choose those. Right? The smaller it doesn't matter what the sector is, because we're not going to write in sectors. We're going to write in blocks, right? The smaller the blocks are, the more things you would end up allocating, right? But don't allocate blocks which are like 1 gigabyte, right? And if you allocate blocks which are 1 gigabyte, then your problem will be extremely easy, because your trace basically would read or write 1 or 2 blocks, right? Doesn't make sense, right? If you make a block to be like, let's say if you make the block to be 4 gig, that's the largest size file you have, right? So essentially that means that all your trace would either have 3 reads or 3 writes, right? And that's sort of bowling. So have more realistic, like 1K or 8K or something like that. Right? You have a lot of freedom in choosing how to do these stuff, right? But you don't have freedom in changing these stuff. You have to read the contents of the disk to modify it. You can't just modify it unless you know what's in there. The only way you know what's in there is if you have it cached, right? If you have it cached, then you have to implement a cache replacement policy. So the first time you come, you won't have the information. So the first directory, you have to create it. Then you have to assume a cache replacement policy. And the TA can expect you to explain what cache replacement policy you used, how big the cache was, and all those things. So I just suggest that you don't do caching for now, right? Caching adds more complications. But if you want to do it, then that's one way to reduce the stuff, right? Does that make sense? Yeah.
So do we just run our scanning for like for example, we're playing C-scan, like we just run that like every time we get like a instruction like 11W, or do we do it for a set of instructions?
You would do it for a set of, you don't care about this part, you only care about what translates here, right? So it's not, I didn't define how often you should run it, right? So essentially you have 1, 2, 3. So you can run it after each request, which is also again boring because there's no choice, right? So you want to wait for some amount of stuff. I'm not defining what that should be, right? So essentially you would run the C-scan on this set of things, right? It can't be 1 because that's a degenerate case. You don't want to wait for the whole thing because I think one of the traces, this is, I think 1024 or 4096000, right? So you're gonna have 4 million entries, right, to run C-scan on. You can do it, but if you don't want to do that, you can say, I wait for 10, 15, 20 or something, and then run the C-scan on the last 10, last 20, something like that, right? Is that clear? So, the next exam is on Friday, and this time it's a true or false plus minus grading, but true or false, 6 questions. I won't be again here for the exam, but this is the last travel for a while. So, yeah. So, are there any questions about what you covered so far? So the exams, yeah.
Is it also it's all the way up to chapter 13, right? Including.
Yeah, including whatever I covered. Right? Yeah. So the next set of exams and the next module would tend to go more towards like tying everything together. So the final exam would be on how would you like design something, how would you place all this decision and stuff, and it will draw from your homework projects and stuff. So like in terms of what you learned, kind of things, right? And it's not going to be true or false. It's going to be you writing some content, and the last exam would be a preparation for the finals in terms of the flavor, right? And like I said before, we also will have classes where we go through them in class, so it shouldn't be the first time we do that. Yeah, I can't think of any other administrative issues, right? So I should still be in email contacts. If you have any questions, send me email, and I should be able to answer. Right. So the next topic, which probably makes a lot more sense for what we'll do with the modern machines, is the notion of RAID. We started discussing that a little bit in the last class, and we'll continue that in this class, right? And one of the things I mentioned was disks are cheap, and you can buy a 250 gig hard drive for practically 60 or 70 bucks, right? And backing up that much of a storage space is hard. I mean, backing up 250 gig onto other media, like such as like DVD or something, would take you forever to back this stuff up. And the market trends are towards larger and larger disks. So the backup problem is only going to get worse and worse. And the disks are getting cheaper and cheaper. And the disks are also getting less reliable in some sense, right? So if you have a faster disk, the faster you go, the more bits you pack, right? It's likely that some of the disks there may be some issues. Disk manufacturers do enormous stuff to make the disk reliable, right? And I think one of the stuff I was mentioning was, you might have read in some of the older textbooks on how fast the disks are actually moving, right? I think it's similar to a 747 jumbo jet flying 1 feet above the runway where the hard disk is going, right? It's supposed to be something like that, some complexity like that. A 747 flying 1 feet above the runway, right? It's even more complicated because it has to fly 1 feet over the runway. It's not allowed to go too far because then you can't read it. If you go too close, then you crash, right? So you have to fly this jumbo jet at 1 feet above the ground, and the disks are only getting faster, which means that you're now going from jumbo jet to say a fighter jet or something, right? And people also tend to move this stuff. So how many of you have a iPod or some device like that, right? there's a little hard disk in there, right? So here the ground moves under the jumbo jets, right? So when you're moving your iPod, the whole platter and all is shaking, right? So imagine flying a fighter jet 1 feet above the ground, always 1 feet, never closer, never far, and the ground is just violently shaking whichever way it wants, right? They're doing enormous stuff to make the disk work. I mean, most of you use iPod and it still works, right? But there are limits of how far it can go, right? And since we can't do a backup into other media, we are trying to. So how does like iPod kind of device avoid this stuff? Do you guys know? You probably heard of the skip protection, right? It has a skip protection, right? What does skip protection do? Yeah.
The hard drive just caches so many megabytes of data, so it can stop if it's moving too much, and you still have data kind of in memory.
It's not caching. It's
Well, that guy's
it is similar, but it's not
okay.
caching. So what is it actually doing? It is similar to caching, but there's a different word for it because it's a different.
Like buffering. I mean, it's kind of.
It's doing read ahead.
Yeah.
Right. Caching is usually you save the contents that you used, and here you're doing read ahead. Right. If you're playing a song, it knows that you're probably going to listen to the whole song, so it reads ahead of where you are and caches that. Right. It does a read ahead and drop behind. Right. So it'll only cache from here to the next, whatever the minute they give you, half minute, 1 minute, 5 minutes, whatever. It'll read from here to the next 5 minutes, and it'll throw away all the stuff from now, all the stuff that I played, right? Because if you have played it, you're not likely to play it again. So in the caching sense, it's inverted, right? In the caching sense, if you just read it, you would keep it in cache. Here, if you just played it, you throw it away. You look for new contents, right? So you do a read ahead, and can you do that on a laptop? Right? If you're carrying a laptop, it's doing the same thing, right? If you're moving your laptop around, can it do a read ahead? So essentially, if you give more money, iPod will keep reading ahead further and further. I'm not sure how far iPod reads, but I think it reads a lot, right? Like 5 minutes or something like that, right? Does anyone know how far ahead iPod reads? It reads quite a bit, right? Can you use the similar technology for a laptop? Why not?
Because, well, you could, but most of the time the user can be doing very unpredictable things. Like, if you're watching a movie or something, then yeah, but typically people are running a lot of applications and switching between them a lot.
Yeah, general purpose operating systems can't always imagine that the user is doing only one thing, right? So yeah, they can do random stuff and you can't really do much, right? Some of you may notice that sometimes your hard disk will freeze. The laptop hard disk will freeze because, like, take your laptop, hopefully it's not, it's under warranty and stuff, and try to kind of, and don't like violently do it, but just like do it like gently like this, right? Your disk will stop, right? And some of the newer hard disk, if you drop the disk, then it figures out it's dropping and it'll shut up the disk, right? IBM was selling it as a feature. I think Apple does that too. If you're dropping it, there's a little accelerometer which figures out it's falling, and it stops the disk. But what it also means that if it thinks it's falling, then you can't read the hard disk because it's protecting itself. Right? So anyway, so RAID issue. So yeah, since the disks are free, we can make copies and stuff, and that's the notion of RAID, right? So the notion here is, if I make a copy of every content I have online, then I can get resiliency because I can go to one of the copies, and that's the notion of RAID. So algorithms that you're going to use for this falls under the general class of algorithms called erasure codes. It's not exactly mentioned like that in the textbook, right? You might have studied about erasure codes in algorithms class. Have you heard of erasure codes before? Right? If you haven't, you may look at it in the algorithms course. So essentially, the idea here is, if you have an object which can be stored on M disk, right? With the erasure code, you want to create m plus n amount of data of the same m data, right? So if you look at it as kilobytes, if you have m kilobytes of data, now you want the data to be m plus n kilobytes. If you look at it as disk, if you have m disks worth of data, you want to create it as m plus n worth of disks, such that even if you lose any n disks, you'll still be able to reconstruct the data, right? So you have to create, so these set of algorithms would figure out a way to distribute it such that you no longer have to look at the m that you stored, right? So now you're creating this mixture. So you need any n of those any m of those to get the data back, or you can tolerate any n failure, right? So that's a good concept. So essentially, you can allow for a certain amount of failures, and you still get the data back, right? And those are a set of things are called erasure codes, and we use that in the RAID array, right? And so actually, I like the pictorial representation of this. So there are the set of RAID levels, and you might have heard about this. And essentially, so the first RAID level 0 is not actually a RAID. It does not give you any redundancy, right? It's called stripping, right? So essentially, if you have 4 hard disks, it kind of glues them together to make them look like one large hard disk. So in the example there, if there are 4 blue hard disks, now if you do it as a RAID 0, it appears to you as one disk, which is 4 times the other one, right? So what are the reasons why you would do RAID 0? Well, let's assume that each hard disk is 10 gig for discussion's sake, right? Yeah.
Maybe performance. Yeah, because now essentially you have 4 read heads and everything moving at once. You can get data 4 times as quickly in theory.
Yeah. So this is one way to get more parallel. So if we have one file system, then now it has 4 different heads to schedule and get better performance. Right? So if you can place the data in such a fashion that all 4 heads are doing independent stuff and getting data for you, then that's good, right?
I'm not sure.
Okay. Yeah, the other reason is you can get a larger disk. If you want a 40 gig disk and you can't afford it, then you can buy 4 of those and then make a 40 gig, right? What are the negatives of this? What are the reasons why you shouldn't do this? Yeah.
You use it for a database or something, and you got a 40 gig database or a 30 gig database, and one of the disk dies, you could corrupt your own database.
Yes. But it's yes. Yeah.
There's 4 times the chance of something crashing.
Yeah. Elementary probability, right? The probability of one disk failing is P, and if you have 4 disks, right? Now, if any other disk fails, your system crashes, so your probability of failure actually goes up, and your reliability actually goes down, right? So RAID 0 is less reliable than each individual disk by themselves, right? So this is not what you want to do if you care about reliability. In fact, if you care about reliability, then you should avoid this, right? Any one disk crashing means the whole system is dead, right? Because the file system is built on top of both of them. Since you want all of them to work together, the data is spread all over the place. There's no redundancy when you fail. The next notion is the RAID 1, which is mirrored, right? Here we have 8 disks, and somebody in the class was explaining this is how they do backups, right? They essentially have a external hard disk, and then they mirror all the contents from the main disk, right? So essentially, everything you write on good set of disks also written on the mirrored set of disks, right? So when the system is running, it actually will have 8 hard disks running perfectly capable of serving your requests at all times, right? But every time you write into one of the disks, you make a copy into the mirrored disk, right? So what are the good things with the mirroring? Well, let's start with what are the bad things with mirroring? Yeah.
You just need twice as many disks, so it requires just a lot of space.
Yeah, you waste twice as many disks, right? Because you have you waste them, right? So in terms of reads, right? What does mirroring do for reads? Yeah.
You can close to double read performance, depending on it.
Mm-hmm. You can double your read performance because you can read from any one of those. So if one disk is busy, you can use the other disk, right? So what would happen to writes? Write means you have to copy to both, right? Yeah.
You gotta write twice.
You can write twice in parallel, right? Yeah, you have to write the same data twice, but you don't have to do it in sequentially, right? So I can write on both disks at the same time, but my write speed won't be faster than a single disk, right? I'll only be able to go at the speed of one disk, right? Because I have to make copies on two disks. Whereas with read, I can actually go twice as fast. If you're reading, block 1, 2, 3, 4 on, 1, 2, 3, 4, 5, 6, then I can essentially read 1, 2, 3, 4 on one copy, 5, 6, 7, 8 on the next copy. So I can get twice the performance, twice read performance, but one level of write performance, right? But the problem is it takes too much redundancy, right? And actually we can do better to get the same amount of redundancy. So the general notion of the erasure code that I was talking about, if you do the m plus n, right? So in this case, you have 4 plus 4. With the erasure code, you can actually fail any 4 hard disks and still be in business, right? Is that true for the RAID 1 mirroring? So why is it different? I see somebody nodding. No, yeah.
Because if two equivalent disks both fail, then you're done.
Yeah, so you don't even need 4, right? If two of them, if the primary and the copy dies, then you are out of business, right? So you can actually do much better than RAID 1, because with RAID 1, if the right set of disks fail, then you are good, but if the wrong set of disks fail, then you could be worse off, right? But many of the laptops or desktops now come with RAID 0 or RAID 1, right? Some of you may have purchased a RAID controller in your desktop because it comes with it, kind of thing. You didn't pay for it, and they do RAID 0 or RAID 1, right? Because for most desktops, you're not going to have more than 2 disks, and there's not a whole lot you can do with 2 disks. So the next set of RAID levels are more complex because they try to do more of the erasure codes. They don't do the full erasure code, but part of it, right? So RAID and RAID 2 and 3 are rarely used. RAID 4 is used in some of the NetApp servers for some reason, and RAID 5 is more common in servers and stuff, right? RAID 2 assumes it's like a memory kind of error checking code where it does not trust any bit. So if you do a parity kind of computation, right? So it uses a lot more parity disks because it's not. So you might have read about parity from architecture class, right? So you can do odd parity, even parity, and certain number of parity bits will give you a certain amount of ability to recover from errors, right? So if you have three parity disks, then you can recover from 2-bit errors and stuff. So you assume that the hard disk has no checking. Hard disk gives you raw data, and then RAID 2 works, right? And it's not really true in modern machines because the hard disk can tell you whether there's a problem with what it read. It can do some amount of basic error checking. So essentially, RAID 2 is not used because you don't need that level of checking. RAID 3 is what is more realistic, right? RAID 3, what it does is you create the notion of a parity, right? I'm not going to tell you how you create that. Assume magically you create that, right? And essentially, this is the erasure code. But the property here is you can recover. So if you have, if you look at the RAID 3 here, It has 4 good disks and 1 parity disk. I should be able to, so if any one of the disks fail, I should still be in business, right? I can read, so if one of the blue disks crashes, I can still use the rest of the 3 good blue disks and the parity disk to reconstruct what I wanted, right? The difference between RAID 3 and RAID 4 and RAID 5 is in the way the parity is computed. In RAID 3, the parity is on a bit-by-bit basis. So essentially what you say is the sector 1 bit 1 of disk 1, sector 1 bit 1 of disk 2, sector 1 bit 1 of disk 3, sector 1 bit 1 of disk 4, all of them are used to calculate the parity bit, which is stored on the sector 1 bit 1 of the parity disk, right? So essentially all the parity for all, bitwise of each disk is calculated and put into the disk. RAID 4 does it on a block by block basis. So you read the parity of one block, parity of another block, right? Do this calculation on a block by block basis and write a parity block, right, on a parity disk. And RAID 5, you take this parity and then interleave it within the data. So there's no separate parity disk. Any disk will have the parity. It's all over the place, right? So now, what are the implications of doing this, right? I'm not actually telling you how the parity calculation is done, and because that's the algorithm part. But essentially, somehow magically, you just need 4 of the 5 to keep going, right? The differences essentially are there because of the way the performance implications are. So let's look at RAID 4, which is more realistic, right? In RAID 4, if I want to read contents, right? If I want to read contents from 4 disks, right? What does RAID 4 do to my read performance? The one thing you need to understand is with a RAID, I don't need to read the parity. I can read any 4 of them to get performance. I don't need to read the blue or the parity. I can read any 4 of them to get what I want, right? So what would that do to my read performance? Thinking back to the mirror right? Or comparing to what would happen if you just have 4 disks. It'll actually make it better. It'll make it just that tad bit better, right? Before I have to read 4 disks worth of content from 4 disk heads. Now I can use the 5th hard disk to get a little bit better performance because I can now read the 5th hard disk and use it to construct the data, right? So if 4 of them are busy, then I can use the 5th one to get data, right? And that's true for RAID 5, and that's true for RAID 4, and that's true for RAID 3. I can now read any 4 of them, and I'm still good to go, right? If I want to check the parity, then I have to read the other one to see if the RAID is still valid. So if I have to check the parity, then I'm essentially as fast as I was before. But if I don't want to check the parity, then I can keep going, right? And so if you do the RAID 5, so the real problem happens when you have to do a write, right? If I have to update a block, so if I have to update a block in, say, let's look at RAID 4, right? If I have to update a block, right, that means, so now you have let's say disk 1, disk 2, disk 3, disk 4, and parity, right? Suppose I want to transpose this to 3 prime, right? Now that means the parity has to go to 3 prime, right? The parity now is the parity of all the data that is stored right now, right? So if the algorithm is good, it can localize this and essentially recompute the parity by reading. So whenever you have to update this file, you have to update this, right? If it's a good code, then essentially you read the parity contents, get rid of the contribution from the old 3, and transpose it to the new parity, and then write it back. So now write would mean I read the parity, I update it, I read the parity, I read the old data, I somehow remove the influence, and then create a new parity, write it, right? So if you have random writes all over to 1, 2, 3, and 4, right? The bottleneck is essentially the parity disk would decide how fast you can go, right? Your parity disk is the bottleneck. And that's why you want to do RAID 5, because RAID 5, the parity is spread all over the place. With the RAID 4, the parity is on one disk, so every time you make a modification, every time you do a random write, you would have to modify the parity disk, right? Every time you do a sequential write, you're still good. You're not that bad, right? If you're doing a sequential write, meaning like if I have to write all 4 at the same time, which is what I would do for peak throughput, right? If I want to get the most performance out of the system, I'm worried about peak throughput. If I'm doing a peak throughput, then I know the parity, because I'm writing all 4 blocks, so I know what the parity is. So I can write all 4 and parity at the same time. So essentially I can keep all the disks busy doing useful stuff for me, right? But random writes, RAID is bad. I mean, these RAID things are bad, right? Which is not really true for mirroring, because mirroring depends on how you insist on doing stuff, right? I can wait for both of them to finish, or I may be able to kind of write one and then have the other stuff pending, right? So I can keep them cached and say, I write all my data to one copy, the other one would be written, not necessarily now, but I can keep going, right? So RAID 5 and all have performance issues for writes, right? Especially random writes. Reads are okay, and maximum, like sequential writes are okay. But random writes would cause the parity as a bottleneck, which is not so much a problem for RAID 5, but it's a problem for RAID 4, right? And RAID 6 is a variant of it, which is more, I mean, essentially you make this n equals 2, right? So now you can have 2 disks failing, and you have 2 different notions of parity. But the main important RAID that you end up using is RAID 1 or RAID 5, right? RAID 1 has a problem if it wastes too much space. RAID 5, so if you have a RAID 5, essentially you get lower wastage and higher performance. But the cost you pay is writes could be a problem, right? So if you're worried about write performance, RAID 5 is not necessarily the way to go, right? And that's one of the reasons why you have variants. So if you look at the literature, people talk about RAID 1001 and all those things. So essentially, if you're creating a database kind of workload and your money is not an issue, you only care about performance, right? RAID and all those things are not necessarily fast. So one of the ways you can do that is RAID 01, right? Which essentially says that you stripe. So if you have 8 disks, you stripe all of them. So essentially, you create RAID 0 of all the 4 disks, and then you mirror those 4. Or you can do it this way. You can mirror two disks and then stripe them across to create. So all this 8 disks will now become 4 useful disk worth of data, right? By using RAID 0 and RAID 1 in certain fashion, right? And each one of them will have different failure rates, right? So which one would you prefer in terms of failures? Assume the 2 disks fail. Which one would you prefer? Yeah.
1 plus 0. Depending on which 2 disks first.
Yeah, if you don't know that, right? If you expect 2 disks to crash, if you want to be resilient across 2 disks crashing, right? What would happen? What's the worst thing that can happen in RAID 0 plus 1 if 2 disks crash? What's the best case scenario for which 2 disks to crash would be ideal, and which 2 disks crashing would be the horrible? Yeah.
2 disks on the same stripe.
Yeah, would be good.
Ideal.
Yeah, and 2 disks on the opposite stripes would be, would not be ideal, right? And about here, yeah, if both the disks on the same stripe fails, then you have issue. But if you Yeah, so depending on where you are and depending on how you expect these things to fail, right, one or the other may be better, right? Yeah, unfortunately, I can't. There's a little bit more slides. We don't have time to finish, right? So, that's the reason why you choose different rate stuff. So you choose rate stuff to figure out what is good for you and stuff. And one other thing I want to add, if you go for RAID 5, right? What happens if one of the disks actually crashes, right? Meaning like it's out of business, so you need to put a new disk in, right? And that's one of the nice things you want to do, right? So if you bring a new disk in, which is completely fresh, right? You have to go through a process of rebuilding, right? Essentially, if you ever done this, it means that your system will now say, okay, now you give me a new disk. I want to recreate the RAID from all the disks I have, right? So what would happen how would you reconstruct the disk on RAID 1? RAID 0 is not really about redundancy, so let's ignore that, right? RAID 1, if one of the disks failed and I replaced it, how would you reconstruct it? Yeah.
Just copy straight from the backup.
Yeah, copy straight from the backup into the old one, right? And the cool thing is you isolate the changes to only the one that failed, right? So if a disk failed, its backup would have to be copying. So the backup disk would not be useful because it's being used to replicate the contents. The rest of the system can still continue to work, right? What would happen for RAID 5? Or RAID 4 or RAID, one of those RAID things? Yeah.
Recalculate the parity and then write the new disk match.
Yeah, so how does it recalculate the parity? Right? It has to. So the way to recalculate the parity is to read all the previous data from all this to calculate the parity for the new disk, right? So if you ever done one of this stuff, right, you'll go through bit by bit for the whole entire disk for all the systems. So if you've seen this thing, the disk light will go, will light up because it's essentially reading all the hard disk data, computing the parity to figure out what the missing data was, and it's going to write it out. So one disk is the new disk is going to be all write, all the other disk is going to be all read, right? So essentially, when you're doing a RAID 5, your system is useless, and it can take actually a long time. So if you have 250 gig and you're doing this, it takes like days or something like that because it's reading all the data, computing this parity, writing all the disk back. And that's a problem, especially that's one of the reasons why you go to 0, 1 and all those things. If you're something like Citibank or something, right? It's good that you're still up and running, but it's not good that it takes you 15 hours to get the stuff back. You're still faster than restoring from backup, but it's not instantaneous, right? Whereas mirroring can be much faster because it's only copying disk to disk. There's no calculation involved. Okay, so that I should conclude the class. That was running a little slow, right? Okay. So the exam should be till here, right? Let me verify that it's still here because I actually gave the exam to the TA. So, but I'll see you on Monday.